something a little bit more complicated. So here now, of course, we have not just a straight beam, but we've got this beam at a weird angle. And we're still being asked to find the normal shear and bending moment at C, which is at this point right here. So let's set up our free body diagrams and figure out which one is the right one to use. It might be intuitive, right? If you look at the one on the right, it's going to have that crazy distributed load. You're going to have to deal with this angle, which I guess you have to deal with on either side. But let's go ahead and draw them out just so everybody is clear. But I suspect that the one on the left is going to be easier. So one, we'll divide and conquer. So we're going to have this thing, and then we have the other version on the right hand side. And a coordinate system for both, of course. Okay, pin at A, so therefore we have AY, AX, and then we have the internal forces. So N is still perpendicular, right? Shear is still going to generate, with respect to the face, right, this kind of a movement. We still want the clockwise rotation for shear, and N is always perpendicular, and then similarly the bending, right, is going to be like this, just like before, where we have the happy moment. All right. On the other side, N is out, shear is up, and M is this way, kind of getting messy. And then we have this distributed load. And then we just have the vertical at B, right? Because it's on these rollers. So which one? I still would say we should go with this one, right? Let's see what that means. Right, so we know we're going to need, let's see, we still need to find AY and AX, right? So we're going to still need to get a free body diagram of the whole thing in order to get those unknowns. I'm going to cheat and use the drawing up here. Maybe not the best. Not so bad. Okay. Again, we have AY, AX, BY, and one nice thing we see right away is, guess what? If we do sum of forces, coordinate system, of course. Sum of forces X, right away we see AX equals 0. Yay! And now, of course, we'll probably need to take the sum of moments at B, but first let's go ahead and replace the distributed load by an equivalent force, just to simplify this. So already we know AX is gone, and let's replace our single uniform load, 2 kilonewtons per meter over the 6. So I'm looking up here at the top, 2 kilonewton per meter times 6, right, is going to give me 12. Am I doing that right? I think so. So we have this distributed load. All right, let's go ahead and put that 12 kilonewtons here. And we can take the sum of moments at B, because really all we care about is AY, right? And we have positive clockwise convention, 12 kilonewtons. And that was acting at 3 meters away. minus AY, and that has a moment arm. Now here, just some of the geometry. Come back up to the top and we see we have this triangle, right? So this is 45, this is 6 meters. So this is 6m cos 45, right? So that's our moment arm for that side, plus then tack on the additional 6. So AY, 6 meters, has a moment arm of 6 meters. Oh, sorry. I don't know why all this is in red. Maybe I can figure out how to edit these videos. Remove all the mistakes. Cosine 45 equals 0. And so there, the only unknown is AY. And so that can be solved for. So now let's assume that that's known. And let's come back to this free body diagram now and figure out what we're going to do about solving for these internal forces. Now this coordinate system is not my favorite, and so it's definitely possible for us. And we know AX equals 0. Now we theoretically have AY. So what I'm going to do is actually just go ahead and rotate it, right? And turn this coordinate system, or turn this diagram. You can turn your paper, or of course, because I'm using that iPad, I'm just going to go ahead and turn this like this. Oops, if I can get it to stay. Try one more time. Definitely going to edit this out. There. And now this angle here is theta. It's the same angle as in the other picture. If this doesn't work for you, then just go ahead and use this version, right? But I like the one on the right because it keeps everything still in the, most things, right, are in the Cartesian coordinate system. That for me just means I don't have to think as hard about doing the calculations. So now we'll use this and solve our equations of equilibrium using this one on the right hand side. So sum of forces in the x direction, n minus AY cosine theta. Do you see what I mean? How you just have to figure out what's going on with AY, right? So n, of course, will then just be AY cosine 45. AY being solved for up here. And then sum of forces y, AY sine theta minus V equals 0. So there's V. So we have normal forces here. Internal normal force, our shear is equal to AY sine theta. Theta is given. And then finally, again, we'll take our sum of moments about point C. I think that's the point given in the problem. Let's go back and check. Yep. So here, convenient spot because then shear doesn't go into, none of these forces are in the equation, right? We just have to deal with the M and then minus the components. But of course, only the vertical component is going to contribute to the moment for AY. So minus AY sine 45 times its moment arm, which we're given in the problem based on where we sectioned it, is 2 meters right here. Equals 0. And so therefore, the internal moment is just AY sine 45 times 2 meters.